Data may be moved between different databases, which is known as data dump tasks. Transfer data between heterogeneous databases, often using text files as intermediaries. However, text files may lose data type information and are slow in speed. When exporting a table to text, some information may be lost, such as long numeric text strings like ID numbers, which may be parsed as numbers during import. In the SPL IDE, data types can be visually distinguished, with the first ID numbers being a numeric type, without an underline, and the second being a string, with an underline. If you need to ensure that the type is not lost, you need to add quotation marks. But when exporting data from the database, quotation marks are often omitted, resulting in inaccurate data parsing. Use SPL to solve this problem. First, retrieve data from the source database using JDBC and export it as a bin file. Then import the data from the bin file into the target database. The bin file is in binary format, which can achieve high-performance data dumping function and ensure no information lost during the process. This script exports the Table 1 of MySQL database as a bin file and CSV file respectively. A2 reads data from Table 1 in the database. A5 reads the data from the bin file, which is of the same type as the source table. The CSV data read by A6 due to the lack of quotation marks resulted in the first value of the ID field losing its data type. Bin files are SPL-specific binary data files that automatically records the data type of data values. When reading in, there is no need to parse and determine the data type, which is much faster than reading text files. Now let's demonstrate a complete example. Taking MySQL and Oracle as examples, we create tables with the same logical structure, both called test001, and insert 10 records as shown in the figure into MySQL. Now we need to dump MySQL data to Oracle. Firstly, export the data from the MySQL database to a bin file. When the amount of data is small, the dbQuery function can be used to return a table sequence. When exporting, it may be the entire table data, or it may be partial columns or data that meet certain conditions, determined by the SQL statement in A2, where the asterisk represents all columns. When the amount of data to be exported is too large to be fully loaded into memory, a cursor should be used to read it. The data export here uses the JDBC driver of the database. When the amount of data is large, it will expose the problem of poor JDBC performance, and exporting is time-consuming. The parallel function of SPL can be utilized to improve data retrieval efficiency, which will be discussed in other videos. Then import the bin file data into another database. When the target structure is the same, this script can be used to implement data import. The option at I in A3 indicates that all data is newly added, and can be imported using the insert method to improve import speed. If the data to be imported has a primary key that duplicates existing data in the table, the original data will be updated directly using the update function without any options. Then the data will be compared with the table, determining whether to use the insert or update method for importing. Sometimes when importing data, it may be necessary to clear the original data in the table first. Then copy the entire data in the file. Option at A means to clear the data in the table before execution. When the target structure is different. For example, some fields in the corresponding file of the table have changed their names. Or there may be newly added fields. You can correspond the field name in the update function, or assign values to the newly added fields. After data dumping, there may be inconsistencies between the data from the source database and the target database, and we need to compare and identify these inconsistencies. Some differences are caused by the rules of the database itself. Observing in dbeaver, it was found that in Oracle, the record with f1 equal to 5 has f2 as null, not an empty string. This is because in Oracle, null represents no value. For string-type data, Oracle considers empty strings as equivalent to null. When using JDBC to write an empty string to an Oracle database, Oracle automatically converts it to null. Before comparison, we need to eliminate the differences caused by these databases themselves. Due to Oracle automatically converting the empty string to null, which is equivalent to losing data information, we can only process the MySQL data by changing all empty strings in F2 to null. Given the field name, SQL can be written directly, for example, the method 1. When only the table name is known, but the specific data structure is unknown, we can first use SQL to return the structure of the known table for its column names and data types, and then dynamically spell out SQL in SPL to convert empty strings to null, such as the method 2. A2 retrieves the field names and data types of the target table from the database. A3 dynamically spell out the select part of the SQL statement. A4 executes the complete SQL, and it can be seen that the F2 value with F1 equals 5 has become null. In order to visually see the comparison results, we made some modifications to the data in the database and artificially generated some inconsistencies. Change F4 with F1 equals 1 to 1 in MySQL. Delete the record with F1 equals 7. Add a record with F1 as 11. Delete the record with F1 equals 9 in Oracle. A common scenario is comparing by primary key, which can be divided into 3 situations. Type 1, T1 does not have it, T2 has it. Type 2, T1 has it, T2 does not. Type 3, both T1 and T2 have it, but there are different columns. The implementation method is to use the join function to perform a full join, and then distinguish between these 3 situations to obtain the comparison result. Because SPL's join function uses hash value comparison by default, while Oracle only has the number type, and does not distinguish between integers and real numbers, returning the decimal type uniformly. The result is that although the values of F1 on both sides are the same, the data types are not consistent, and the calculated hash values are also different. Convert the values of F1 from Oracle to integer, and set MySQL table to T1 and Oracle table to T2. A6 identifies the first scenario. T1 does not have the record, but T2 has it. A7 identifies the second scenario. T2 does not have the record, but T1 has it. In the third scenario, in order to find records with any different field, A8 uses macros to concatenate expressions, and the resulting expression looks like this. By executing A8, the records can be obtained that the primary keys of T1 and T2 are equal, but there are differences in other fields. When dealing with small amounts of data, the results will not be very large and can be viewed directly without the need to export to a file. When there is no primary key in the tables to be compared, it is necessary to perform a full column data comparison. However, there may be differences in the column names of the tables. In this case, macros can be used to spell out the SQL to be executed for each database separately. A2 retrieves the field names and data types of the target table from the MySQL database. A3 dynamically concatenates the select part of the SQL statement, while A4 actually executes the SQL as follows. Similarly, A6 retrieves the field names and data types of the target table from the Oracle database. The SQL actually executed by A7 is like this. Full column comparison can only find data that may not match any of the fields on either side, so the macros used in A8 are the full column names of the table sequences returned by A4 and A7. A9 finds records that T1 does not have but T2 has. A10 finds records that T2 does not have, but T1 has. When the amount of data is large, it cannot be read into memory for full join anymore. The data needs to be sorted by comparison field, and orderly merged to implement full join. Therefore, order by needs to be added to the data retrieval cycle to ensure that the retrieved data is sorted by the primary key. When the amount of data is large, the comparison results may also be too large to be loaded into memory. At this point, it is necessary to write the data in the cursor to a file. A7 writes the data from A6 cursor to T2btx file, where it represents writing it as a bin file. This is the first scenario, finding records that T1 does not have but T2 has. Using the same method, when there is a large amount of data, identify the second scenario. That is, finding records that T1 has but T2 doesn't have. Here is the third scenario. The primary keys of T1 and T2 are equal, but the other columns are different. Similar to small data amount, A7 requires the use of macros to spell out conditions where any column is unequal, like this. But there is a problem. Unlike small data amount, a cursor can only be traversed once, so only one scenario can be calculated each time. This approach is too slow. It's like traversing the data 3 times. SPL provides a channel mechanism that can filter these 3 conditions in one traversal. Continuing with the script on the previous page, starting from A6. A6 is the result of matching 2 tables by primary key and is a cursor. Create 3 channels from A7 to A9 respectively. Then attach operational functions to the channels. A10 finds records that T1 does not have, but T2 has. A11 finds records that T2 does not have, but T1 has. A12 finds records that the primary keys of T1 and T2 are equal, but there are differences in other fields. A13 traverses A6 cursor. This is a one-time action. Finally, obtain the results of additional calculations for these 3 channels. Exporting data from the channels to a bin file can be done by adding the parameter f to the chfetch function, like this. There are also cases of full column data comparison for large data amount. Similar to comparing with primary keys, data sorting is also required, but the difference is that sorting should be targeted towards the entire columns of data. The SPL concatenated by A4 is like this, where all columns participate in sorting. The SPL concatenated by A7 looks like this. Finally, the data is orderly merged to implement full join, and the results of both scenarios are exported to a bin file using channels through one traversal. Sometimes, it is necessary to compare 2 files, similar to the situation of databases. The difference is that when the amount of data is large, the data sorting action changes from the database's order by to using sortx in SPL. Taking big data amount full column comparison as an example, 2 CSV files, A and B, store the data from MySQL and Oracle's test 001 table. The above is all the content we need to learn about SPL's data dumping and comparison. With SPL, we can easily implement database dumping and compare the dumped data conveniently. Of course, SPL's capabilities go far beyond that. SPL also supports text computing, SQL migration, mixed database and other non-database computing, and can use SPL's computing power to optimize SQL performance. We will gradually introduce these contents in the following practice series. SPL is an open source software that can be obtained from GitHub.